Welcome back to Computer Science 4300. Today's lecture, finally, we get past all of that intro stuff. So we looked at C++ and some SFML, and we gave assignment 1, which was really just, getting used to C++, getting used to SFML. But this lecture today is where we start to introduce the actual real content of the course. And that content of the course is going to be the ECS programming paradigm or programming architecture that we're going to use for the entire game engine going forward. So today we're really introducing that topic. So it shouldn't be too long of a lecture, but let's just get started on it and see how it goes. So let me swap over to my slides. Here we go. So lecture 5, Entities, Components, and Systems, or ECS. And at the very end of this lecture, we're going to talk a bit about the vec2 class, and then I'll go into a little bit of a live programming example and make this class that we're going to be using for the rest of our semester for storing data. Okay, so this is a little bit of a review of what we did the first time and then some new information. So ECS game programming. Why do we want to use ECS for games? Well, we can use ECS for a lot of different things, but specifically, why would we want to use that for games? Well, ECS stands for Entities, Components, and Systems. An entity is essentially anything object. Any object in the game. So a player, a platform, a tile, a bullet, an enemy, lots of different things, or basically anything in the game that has a position or can move around or we can interact with it, that is an entity in the game. So ECS is actually a software design paradigm or a software architecture paradigm, and it's a composition-based paradigm, meaning that we're going to have entities that are composed of components. So let's go back a little bit and we'll look at what I'm calling object-oriented design. So object-oriented design for games is not quite the same thing as object-oriented programming. So let me first differentiate the two. So object-oriented programming is programming with classes and inheritance or polymorphism that allows us to be implementation efficient when we try to implement our classes. Object-oriented design for video games I would define as like trying to structure all of the things in our game, like tiles or the player or enemies, in an object-oriented hierarchy. So there's a little bit of a difference between object-oriented design and object-oriented programming. So at its root, object-oriented programming and the theory behind object-oriented design, they're designed to help us manage data and manage code. So in OOP, an entity would be any object in the game. So for example, since each entity in the game has at least one property in common, that is, since it's a 2D game, it will have an X and a Y position, what we'll do is we'll create an entity class, that's the base class for the hierarchy of everything in our game, and that entity base class will have an X and a Y position. And then things like tiles and players and enemies and bullets, they will all inherit from entity, and then they will add the data that is specific to them. So for example, a tile may have a sprite associated with it. A player may have like an input associated with it, etc. So what we end up with is this hierarchy of classes, where at the top we have a base class entity, and then let's say, for example, we wanted to for optimization purposes, differentiate between static enemies, or static entities, such as trees and rocks, and dynamic entities, such as enemies or the player. Well then, what happens when we want to have like an evil tree, right? So maybe there's a tree that's an enemy inherited from dynamic, but tree inherits from static, and so it gets, like, what do we even do in this situation? It's really difficult to maintain this hierarchy in a way that makes sense. And if we have tons of different things that we want to create in our game, then we're going to have possibly like dozens or hundreds of different classes, and the code becomes unmanageable, etc., etc. So object-oriented design for video games is not the best way to go about it. Let's look at entity component architecture instead. So in entity component architecture, an entity is any object in the game, and then a component is just some data or properties that we can attach to entities. So for example, one component might be a position in the map, or the current speed that we're going, or a bounding box, or health, weapon, damage, etc. So anything you can think of that some entity in your game may want to have, then that's a component that can be attached to an entity. So we can consider entities as, in implementation-wise, just as some sort of container structure that's going to store components efficiently. So if we look at the same example as before, except now in an entity component way, so before, recall that we had this hierarchy, this vertical hierarchy, now we have this real horizontal structure where we just, whenever we want to create something, we just pick and choose from the components that we want to create that thing. So for example, a tree would just have a position and a sprite. Okay? An enemy, like a Goomba or something, might have a position, an AI, a sprite, a bounding box, and a velocity. And a player may have all of the same things as an enemy, except instead of having an AI that controls it, it's going to have an input that controls it. So in this way, we can create hundreds, if not thousands, of different types of entities just from having a few different component classes that we can mix and match together in different ways. And so, for example, if I wanted to have gravity in my game, all I would have to do is have a gravity component and then attach it to whatever I wanted in my game to fall. Okay? And in that way, we don't have to create like an enemy class and then an enemy with gravity class that inherits from enemy class and all that kind of stuff that might get really, really cumbersome to maintain. So this is the real key to entity component architecture. It's that components are just data, and we attach that data to entities. And then systems later on will work on this data to accomplish the mechanics of the game that we want to actually happen. So ECS game programming. As I said before, ECS uses composition-based design. We are composing entities out of components. So an entity is any object in the game. A component is a property that you attach to entities. And the important thing here is that components are pure data. And systems are the code and logic that drives the behavior. So for example, we might have a function that does all the movement in our game. We may have a function that does all the rendering or the sound or the physics. And so those systems take in entities, they read the components of the entities, and then they do the logic based on that. Now, a really important point is that a lot of places out there will, or a lot of games out there, they operate on what I want to call EC systems. So we are using ECS. Some places use EC systems. So I know it's a really fine detail. So ours is like E, C, S. And another thing you might see is like an EC, system. So the difference is that in the EC architectures, components contain logic, okay? So your component classes in an EC system might contain, for example, the code to update the position of that component. However, in pure, if I can use air quotes, pure ECS, components are pure data and contain no logic. So if you ever see like someone say entity component system, right? It's a little bit different from entities, components, and systems. So I know it's confusing, but there's just a small difference there where in some situations, I think Unity used to operate like this, where the components contain the functionality as well. But what we'll be doing for this course, just to repeat, is that all of the logic are contained in our systems and there is no logic in any of the components. So again, here are some examples of ECS composition that we might have in our course. So an example here for a player, well, a player and an enemy, maybe they both have a position, maybe they both have a speed, a bounding box, a sprite, and a health. However, maybe the player is affected by gravity and has an input versus the enemy that just has an AI. My mouse drawing is absolutely terrible. I'm sorry for those circles. That was brutal. A bullet, on the other hand, might have a position, a speed, like an angle that it's currently going at, a bounding box. Maybe it has a sprite for drawing and a damage and a lifespan, versus something really simple like a tile may just have a position, a bounding box, and a sprite. And you can just imagine how many different things we can make out of these components and how difficult that may be to maintain a hierarchy if we were using object-oriented design. All right, so just a couple of examples of systems in ECS. They're pretty simple for the most part. I mean, for example, the movement system for entities might be, okay, just take the speed of the entity for each entity and add it to its position. There you go. So we've looked up all the entities. If the entity has a position and it has a speed, add the speed to the position. That's how we update the position of all our entities. Similarly, let's say we have some sort of collision system. So we could say, okay, we want bullets to collide with enemies, right? So we say for each bullet, then for each bullet, we look at each enemy, and we call our physics system, and we say, physics, if there's a collision between the bullet and the enemy, then the enemy's health is reduced by the bullet's damage, and then we destroy the bullet, okay? And in this sort of system, you can see, like, maybe we don't want the bullet to be destroyed, and so maybe the bullet goes on and on through multiple entities. If we want that to happen, then we would just not destroy the bullet. So these systems are super powerful because they allow us to do a whole bunch of different things really easily. And similarly, our rendering system would just say, well, go over each entity, take the sprite of that entity, and then draw that sprite at a given position. That's it. So that's just an example of some systems. So then our game engine architecture is going to look something like this. Up at the top level, we're going to have a game engine class. That game engine class is going to hold a number of scenes, and we're going to get into scenes a bit later in the course. The scenes are going to contain the systems, because, for example, what a scene is, how I define a scene is a portion of gameplay in which the mechanics of play are very similar. So, for example, you might have a menu scene, like a main menu scene, where all you're doing in the gameplay is just moving up and down in the menus and choosing different options. The gameplay on the menu scene is going to be dramatically different than like the playing a Mario level scene, right? So maybe we have a play Mario scene and we have a main menu scene. And so the game engine is going to store those different scenes and then transition between them based on whatever logic we have. And then those scenes are going to store different systems. Like the menu system might not have to know anything about gravity, right? Or shooting bullets. Whereas the Play Mario scene doesn't need to know anything about how to move a cursor in a menu. So the systems are going to be at a per scene level. And then the scenes are each going to have their own entity manager. And so the entity manager we're going to get in the next class, but it may be the most important part of this entire architecture. Because in video games, what's happening is our entities are moving around, we're going to be shooting bullets, we're going to be spawning enemies, we're going to be killing enemies, and so the lifetime of entities in our system is going to be pretty complex. And we're going to create this entity manager system that allows us to just say, hey, entity manager, create a new entity for me. Hey, entity manager, destroy this entity for me. And so this entity manager we're going to be talking about the factory design pattern for software design, and we're going to implement a factory for the entity manager, and then the entity manager is going to store all our entities, and then our entities are going to store our components, okay? So this is the game engine architecture that we're going to use until the very end of the course, where I talk about how this could possibly be improved if you were going to actually like really low-level optimize things for like a AAA game or something like that. Okay, so what is a component? Well, we talked about this a bit already. I just wanted to have an extra slide. So an ECS component is just data. We may have like a little bit of logic in the constructor, but there is no helper functionality within the components. A component class has some intuitive meaning to an entity that contains it. So our components are going to be named in such a way and organized such that they like correspond to some sort of gameplay mechanic. So we might have a position component. We may have a gravity component or a health component. We wouldn't just have an X component, right? Because that doesn't really describe things. And so how are we going to implement those in C++? Well, we'll see that as we go through the course. We're going to start out with like the simplest possible implementation of components and how they're stored within entities. And then from assignment to assignment, we're going to make gradual improvements on the storage of components. So what is an entity? Well, an entity is any object in the game, and usually it's an object that has a position. So there's no unique functionality on an entity. The entity just lives and dies and stores components. It doesn't know anything about like what type of game is being played, or that things can move around, or that bullets can be shot. An entity is essentially just a container for components. And a really important thing is that an entity is going to store at most one of each component type. And we'll see why that matters a little bit later. Exactly how components are stored and used within an entity can be a little bit of a complex topic. We're going to go through a couple of different options. So the first option for component storage is that since there'll be at most one of every component, we can just store a variable for each component type. So for what I mean by this is that an entity is only going to have one position. It's only going to have one health. It's only going to have one bounding box, right? And so all of the components are designed such that there's only going to be one of them. But you may say something like, well, Dave, what if we have like an item, right? Maybe an entity holds more than one item. Well, in that case, what we would have is an entity would have an inventory component, right? And that inventory would store multiple items, rather than having multiple item components. So the fact that an entity stores exactly one of each component is very important. The second way we could do this is instead of having a variable for each component type, we could store some sort of single container of components. And then we could make functions like add component and get component for more generality than just using individual variables. So let's look at what that might look like if we actually implemented it. So the simplest possible way that you could store components inside an entity class would just be to have pointers to those components within the entity class, right? So an entity is going to start out, for example, let's say we have a simple entity that just has a transform. So we're gonna be having a transform component, and transform just means position, speed, acceleration. They're all stored within the transform component. Maybe it has a transform, it has a name, it has a shape, and it has a bounding box. Okay, so it's going to have at most one of each of those things. And so it's going to store a component pointer for each of those and set those equal to null pointer. And then the constructor wouldn't have to do anything. But the kind of annoying thing here is that because we're storing raw pointers in this entity, we need to free the memory properly when we destruct this entity class. Okay. We are not. Let me make a change here. So I had a typo on that slide. Okay, so this is the simplest possible way to do it. However, the annoying thing about this is that we have to manage our memory properly, and we really don't want to have to worry about that. So what we did in a previous class was we talked about smart pointers, or in this course, we're going to use shared pointers, okay? So instead of using raw pointers to these components, we're going to just use shared pointers to these components. And now some of you out there who are more familiar with C++ are going to say, why don't you use unique pointers versus shared pointers versus whatever? Shared pointers, we're just going to use them for this course. And just know in the future that there are data structures that are a little bit more efficient than shared pointers, but I don't want to bog down the complexity of the course with details like the difference between shared pointers and unique pointers and all that. So our entity, and this is what we're going to use for assignment 2, we're going to have an entity class that stores shared pointers to all of these types of components. And our entity constructor is just not going to do anything. And the cool thing is that because shared pointers implement RAII, which we talked about in a previous class, then we don't need to worry about the memory management for those. So the destructor here, we can just use the default destructor and the memory will all be cleaned up for us. As we keep going in the course, we could think about, okay, well, this is kind of annoying. Maybe we have like 40 different components, right? And we don't want to have 40 different variables and then have to keep track of all those variable names and stuff. And so we could think about something like this, where we're maybe going to have some sort of container of components, and then we would have public getter functions that let us do things like add a component or get a component. It turns out that through multiple years of offering this course, I have found that we don't want to use a vector for this. What we actually want to use, which will make life much easier for us, is going to be a C++ tuple. So this tuple is just a data structure that can store multiple types, multiple unique types. And we're going to be able to very easily, with a tuple, do things like add component and get component. But I don't want to get too ahead of myself. We're going to do this one later on in the course, I think maybe in assignment 3. Okay, but just know that that's going to come at some point in the future. I just want to start you off slow and then build you up to more and more complex entity storage that has its own benefits later on. So how will we implement our components then? In this course, we will have different component class for each component that we want to implement. And what I'm going to do is I'm going to have a naming convention, which is C component name. So for example, C, that first C stands for component, and then the name of the component is going to be, for example, C transform. Or C health, or C gravity, or something like that. And it's very, very easy to implement the entity component storage option number 1 with this. And we'll come back to number 3 or number 4 a bit later in the course. So here is what our transform component is going to look like. Now, so this transform component is very, very short. There's not much to it. And the reason that components are so simple is because they are pure data in ECS. So what does it store? Well, all of our components are going to store publicly accessible data. Now, you may have been taught in the past that whenever you're using like classes, you want the data to be private for information hiding purposes, and then you have getters and setters for that data. But it turns out that in this course, we're going to have like 10 or 12 different components, and we're going to be accessing that data so frequently that we may as well just make the internal variables public. Okay, so here I've got a naming structure that whenever it's a private variable, it's m underscore, but whenever it's a public variable, there's no prefix. And what we have here is a vec2. I'm going to get back to what vec2 is at the end of this class. We're going to fully explain what vec2 is. But essentially, vec2 is just a point. It's an xy point in space. So a transform component would hold something like the position of the entity and the current velocity of the entity. And then the constructor, maybe you have a blank constructor here that just sets things into 0, or you want to also have a constructor which takes in a position and takes in a velocity and sets those things correctly. And so this constructor here, that's going to be pretty much the most logic that we ever see inside a transform. And it's not really logic, it's just allowing us to set the data a little bit easier. Here's another example. Here's a shape. Oh geez, I've got this like coming in one by one. So here's a very simple class that we'll use in assignment 2, a shape, right? So let's say that we have a class shape, which is C shape, and our public component here is just an SFML circle shape. And then what we can do later on is when we want to draw the component, we can say, well, if it has a shape, let me just take the shape and draw that to the window. Okay, so really, really simple. Our components end up being really, really simple to understand and reason about. So recall this is what our entity looks like, right? So we've got our entity constructor that pretty much does nothing. And we've got our components that are internal to the entity that we can access publicly. I just had a question. Are these class names sort of like the canonical way of naming things in C++? C++ doesn't really have a canonical way of naming things. A lot of people, like in their C++, they like to use like uppercase first, camel case, and almond brackets, and so I'm just going with what I'm familiar with and what over the years I've found works best for me and works best for students and the markers, and is also some sort of industry standard in some way. So there's no single way to format your stuff or name your stuff in C++, but certain companies may have their own way of doing things, and this is just what I'm using for the course. All right. So if this is what an entity looks like from the inside, how are we actually going to use an entity in our code? What does it look like to actually instantiate and use an entity? Well, here's what that looks like. So maybe we have our main function, and we are going to have some sort of container of entities, right? Because I'm going to have some bullets, I'm going to have some players, some enemies, whatever. So what I'm going to do is I'm going to set up 2 points, or 2 vec2s. The first vec2 is a position. So here we say vec2 p for position, just because I want to save on horizontal space. So the position is going to be 100 in the x and 200 in the y, and then maybe the velocity is going to be 10 in the x and 10 in the y. Then I'm going to set up an entity, so just entity E, I can declare an entity. Then I'm going to say the C transform component of the entity, I'm going to construct a new transform, okay? And the way we make a new shared pointer the correct way in C++ is by invoking standard make shared. So if I've got a C transform, which takes as input parameters to its constructor a position and a velocity, then it's really easy to construct this thing here. I just say e.cTransform equals standard make shared, and then the type of the transform, and then p comma v. All right. Similarly, if I wanted to set up the name of that transform, I could say e.cName, so that's the name component, equals standard make shared cName, and as the constructor to that, I can say redbox. And I've just put in some spaces here between the template argument and the parentheses just to make it a little bit easier to read. And then maybe I also have the shape. I'm going to make shared C shape with the arguments. All right. So entity, and then once I'm done setting up this entity, and then I've set the properties of the entity, then I can take this entity and put it into the vector. And then I'll do stuff with those entities, right? So now I've set up a bunch of entities, I've put it into the vector, and now I want to do some things with those entities. Someone in the class said, why using standard shared pointer not correct? So standard shared pointer, you can invoke it with its own constructor. You could say e.cTransform equals standard shared pointer, but then as the input parameter to the shared pointer, you have to pass a pointer. And so you either have to call new in there, or you have to pass in another pointer, and it's not the preferred way of doing it, because by doing it this way, you are 100% certain that the shared pointer is going to have full ownership of the raw pointer internal to it, and nothing else can ever access that raw pointer. So the reason we use standard make shared is for safety, C++ safety. Okay? And if you don't understand all of that right now, just trust me with it, use it this way, and then later on when you get more familiar with shared pointers, you'll understand why we did it that way. Okay, so down here, let's say now we have a vector of entities. How about we do some things with the entities? Okay, so do stuff. We're going to take in a, remember, we don't want to copy our vector when we pass it into this function. We want to be able to modify the entities in this function, and so we pass in a reference to those entities. So the way in C++ that I can really easily iterate through the entities in this vector is to just do a range-based for loop. So for auto reference E, this is basically, I could have typed entity here, but auto is just shorter. Excuse me again. So for auto reference E in entities, now just as a quick aside for C++, if I left out this reference here when I do a range-based for loop, then what will happen is I am actually creating a copy of every entity. And if I create a copy of something and then modify the copy, then the entity that lives in this vector will not be modified. And so this whole function will be for nothing. Okay? So I have to make sure that I'm iterating over references to the entities so that when I modify the position or speed of these entities, that I'm actually making changes to where all the entities live. So for each entity, well, let's say that I just want to move the position, or I want to move the entity based on its current speed. And velocity here is essentially a two-directional speed. So our speeds in this game are going to have an x and a y component, and a vector of speeds is a velocity. That's why that's called velocity. And so all we have to do is we take the transform of the entity, grab its position, and then we add the velocity to that. And I cannot believe that I forgot to tell you what this arrow thing is. Oh, geez. Now I'm going to have to go do that. So, why didn't I say that before? Whenever I refer to the internal variable of an object, so for here, example, whenever I refer to the internal variable of an object or a reference to an object, I can use dot. But when it's a pointer, and a shared pointer is a pointer, I have to use dash greater than. So that's just, we call it the arrow. And so whenever you see an arrow, you know the thing to the left of it is a pointer. All right? So I can't say C transform dot pos because C transform is a shared pointer. All right. So it's the syntax for accessing the internal variable of something that is a pointer. All right. So I won't go too deep into that. You'll get used to that. Then what I have to do with SFML, at least, is I have to, now that the position of my entity has been updated, the internal shape that I want to draw, well, I'm going to have to update the position of the shape to match the position of the entity. So I can say e.cshape, right? Because that's how we stored the shape in our entity. And then we'll get the shape variable from the cshape component, and we'll set the position of that variable to be equal to the position of the transform component. And then all we have to do is say window.draw, and then we get the shape from our shape component. And that's it. So these 4 lines of code that's how we go through all of our entities. We get the speed of the entity, we add it to the position to update its position, and then we set the position of the shape, and then we draw the shape. Okay. Yeah, so someone just pointed out that I have a typo on this slide, and that's a good catch. The typo was that I had a capital C here for C transform, and C transform is the name of the class, not the name of the variable. And so that was a typo, so I just fixed that. And it's a typo down here as well, so I'll fix that for the slides. So this is why I don't release the slides ahead of time, is because sometimes the really good people out in the chat will tell me that I've made typos. And of course, all of my typos are intentional just to see if you're awake out there, right? At least that's what I'll say. Okie doke. So let's look at systems now. So this do stuff, this did a bunch of different things. It updated the positions, it set the positions of the shapes, and then it drew the shapes to the screen, right? Our systems in ECS are going to be really neat and tidy because we are going to separate them by functionality. All right, so let's look at that. So what we can have, let's say we have a movement system, and I'm going to put a lowercase s just to have system for movement. So S movement, that's the movement system. The movement system is going to take in all the entities, and it's just going to do the moving of the entities, okay? So for each entity, again, I'm going to take the position and add it. That's it. So that's the movement system. Now, if we have gravity or acceleration, we may have another line or two in here where we take the acceleration and add it to the velocity before adding it to the position. But it's pretty simple, right? And this is really good because we want to separate functionality of our systems into the easiest possible things to comprehend. So some systems are only going to operate on entities which contain certain components, right? So for example, our movement system will only operate on things which have transforms, right? Because if they don't have transforms, then they don't have positions, and so it can't have movement. Our rendering system will only operate on entities which have both transforms and shapes, because if there's no shape associated with it, then we can't render it, right? And when we get into future assignments, this will be, instead of just a shape, it'll be a sprite with some graphics data. Similarly, our physics system only wants to operate on things that have bounding boxes, right? Because the bounding box is the thing that tells our physics systems when things collide. And so we can filter entity. Whenever we make these systems, we can do this one of two ways. We can either filter the entities just before we pass them into the system, or when we're in the system, we can iterate over all the entities and only do things with the ones that have the components that we want. So again, just recall that for the time being, this is what our entities look like. And so when an entity is constructed, we essentially have all of these blank shared pointers. And when you default construct a shared pointer, by default, it's equal to null. Okay, so the internal pointer of a shared pointer that has not yet been set up is a null pointer. And so if you want to check if a component has, oh, there's a typo here too, and it's probably on all my slides if it's on this one. So that T wasn't capitalized. If you want to check to see if a component has been added to an entity, then what you can do is just check to see if the component is null or not. Because if it hasn't been added yet, it'll still be null, and if it has been added, then it won't be null. All right, so if we want to check to see if an entity has a component, how do we do that? Well, let's set up an entity. So it's just a basic entity, and we're going to set up the name variable, so the name component of the entity. So we've given it one, right? That component, the CName component, is stored as a shared pointer. And so by default, it's a null pointer, or 0, and in C++, 0 means false. Anything other than 0 means true. And so this is a great shortcut that lets us do something like this. So we can say if e.transform, and that checks to see whether or not the transform component exists inside this entity. So because this entity here does not have a transform component yet, we can say if e.cTransform, and that will evaluate to false. Okay? Because it's currently a null pointer. A null pointer has an actual integer value of 0, and in C++, 0 means false. If we say e.cname, if e.cname, it has been set up, its pointer value is non-zero, therefore it will evaluate to true. So I can say if e.cname, print out the name, or do something with the name. Similarly, if we were rendering something, right, and we wanted to see, does this entity need to be rendered, or is it possible for me to render this entity, I can say if it has a transform and it has a shape. So if it has a transform and it has a shape, then I can render it, right? I can render it at the position with the given shape. And there you go. That's how we check to see whether or not an entity contains components, at least within the architecture that we're going with for assignment 2. Once we go into assignment 3, we'll have a different architecture for entity and we'll use a slightly different method. But I think it's good to start here and use this method because it's the simplest possible method. It gets you up and running using entities without having a bunch of other code that you don't need to worry about. And it's sort of, this is our story, right? It's our journey through game programming and our journey through ECS. And we've got to take those first few steps. We don't want to just dive in right away and have the final architecture already done up. And it also is going to show you, in my opinion, once you've used this, even though it's simple and it works, what the benefits are of using the system we'll have at the end, right? Okay. Someone asks, just to make sure, in this implementation, every entity will technically have every component, right? Yes. And forever, well, it will have place to store every component, okay? And that's the thing. Technically, no matter what, even in the final solution in this course, the final architecture, each entity will store each component. It just will. And whether or not it actually contains a component is whether or not it has been set up yet. Okay? Now, you may be rightfully thinking at this point in the course, well, what if the vast majority of my entities don't have shapes or bounding boxes, right? Then I'm using a lot of extra storage for this. Well, turns out we'll have a look at that at the end. And yes, this does waste a little bit of space by allocating pointer data for things that we haven't used yet. However, this is, like I said, it's the first step. It's not the most efficient thing. It's the thing that's allowing us to start using ECS. So we will, toward the end of the course, we'll start talking about how we can make this storage system more efficient and all stuff like that. But I don't want to bog you down with weeks of optimizations before we even get into it. Alrighty. So that is that. So let's have a look at what a system might look like now. So here is our rendering system. So our rendering system is going to get passed in a vector of entities, and then we're going to loop through those entities, and we're going to say if the entity has a shape component and the entity has a transform component, then I'm going to set the position of the shape to the position of the transform, and then I'm going to draw the shape of the transform or of the component. And that's it. So that's our rendering system. Now, of course, you're going to have more special effects and stuff, but this is how you draw every component going forward in the course. Or sorry, every entity going forward in the course. So here's what we end up having at this point. We have entities, right? Entities are going to store some number of components. So here, for example, we have size, we have gravity, and we have position. Then, in our main game loop, we're going to have a number of systems. So maybe you have a gravity system, we have a movement system, we have an input system, we have a rendering system. Each system is going to look at all the entities. It's going to say, for example, the gravity system will say, does this entity have gravity? If yes, then it's going to look at the gravity component for that entity. Then it's going to update the coordinates of the position based on the gravity, and then everything goes into the next system. And that repeats for each different system. Okay? So it's a pretty simple, intuitive system, and we're going to wrap all of this in some nice classes and make it nice to use, and that'll be assignment 2. Okie doke. So that is sort of the first half of this lecture. And the second half of this lecture, I want to come back and talk about the vec2 class. Now, first of all, you may say, but Dave, SFML already has a vector2 class. Indeed it does. That's a good observation. Why don't we just use the built-in vector2 class? Well, the reason we don't want to do that is because I want you to learn a little bit of C++, and also I want to show you just how powerful we can make our own vec2 class. So we're going to put a bunch of functions on it like distance and length and all sorts of different functions that I can't remember at the moment. But we're going to implement our own vec2 class with addition and subtraction and multiplication and dot products and all sorts of cool stuff. So we're doing it sort of just because, but that just because is for educational purposes, right? So it's not just busy work. It will end up saving you time in the future. So vectors in games. Why would we want to use a vec2 class? Well, for 2D games, many quantities and properties of a game object have both an X and a Y component, and these form a vector. So when I'm talking about vectors here, these are mathematical vectors, as in like multiple values that are all tied together somehow. This is a mathematical vector, not a collection vector like you would have in the standard template library or in Java or in Python, okay? So these vectors that we're talking about right now are mathematical vectors. So for example, in our game, we may have a position vector, which is an XY, and a velocity vector, which also has XY. And it would be really annoying to store and refer to like two variables for the position. So of course we could have like position X, position Y, and velocity X and velocity Y. And then we have 4 different variables, and we have to remember the names of all those variables. And so what we're just going to do is we're going to make our own 2D vector class, and that's going to be called vec2. So just a quick note is that we're going to go more in depth on vector math a bit later in the course. In fact, in the next lecture, I do have some vector math that I want to go over. But first, we're going to introduce the programming architecture that we want to put the vec2 in. And then later, we're going to use vec2 to implement all of our physics systems and stuff like that for our game. And so, as I said before, the SFML vector2 already exists, and essentially, we're just reinventing it for this course, okay? So what sort of variables do we want to store in this vec2 class? What will it contain? Well, it essentially just needs an X and a Y component. What do we want to do with those values? Well, we're going to want to have things like, maybe I want to add 2 vec2s together, or I want to subtract them, or I want to divide, or I want to get the distance between them. So we're going to have a bunch of functions and operators that we put into this vec2 class. For example, we could have addition, subtraction, multiplication, division, whatever division means for vectors. We'll see that later. We could get the length of a vector. We could normalize a vector. We could rotate it, etc. So what our vec2 class is going to look like is something like this, where we're going to have public X and Y variables, and the reason for that is just because we're going to be referring to them so often that we just want to have these public variables that we can use. We're going to have constructors, so maybe we have a default constructor that just leaves things 0. We have a vec2 class that we have a constructor that takes in floats. We're going to have an operator. So this operator equals, where we take in another vector so we can say like our 2 vectors equal, we can add 2 vectors, etc. And then how we would use those vectors is something like the following. So we could have like a position, a speed, acceleration, and then I could say, while I'm in my game loop, add the speed to the position and add the acceleration to the speed. Later on, if I want to know like how far something has traveled, maybe I have a distance, which is the length of that vec2. So rather than just talk about vec2s, why don't we go implement one? So I'm going to do that, and we can do that. I'm going to open up assignment 1. Why not open up assignment 1? So let's go back to the middle monitor here. Okay. So, oops, my phone is dinging. All right. So this is assignment 1. And as we saw with assignment 1, we had things like circle move speed. We had things like we were updating the positions of things. So let's just program in here, and we're going to make our own vec2 class. So let's just do that from scratch. Why don't we? All right. So class vec2, I guess I should capitalize it because that's what it is in the slides. So class vec2, we're going to have public, we're going to have a float x equals 0, and a float y equals 0. So those are going to be our public variables. Then we're going to have a constructor, the default constructor, and we are going to have a constructor that's going to take float, x in, float, y in, and we are going to use our initializer list to say x gets the value of x in and y gets the value of y in. All right, so I can use this as it is. So let me first, I'm just going to come up here and return. This way we're not doing any of like the animation stuff. We just want to use this vec2 class. And I forgot to add some braces to that. There we go. So let's set up a vec2, and this is going to be v1, or let's call it p1, and that's going to be 100, 200. And then I'm going to standard cout p1.x, and then a space, and then p1.y, and then a new line. All right, so this is really pretty simple. We're just going to run this program, and we're going to get our output. Oh, so nope, main has to return a value, return 0. Okay, so you can see here when I ran that program, I get the value 100, 200. Okay, so x 100, y 200. Now, I may want to print out things in the future, right? So what I can do, maybe I just put a function onto the vec2 class, which is print. So here, I'm going to go bang, bang, bang. So this is going to just be the x, and this is going to be the y. All right, so here, oh, I haven't actually printed that, so now I can call p1.print. Perfect. Let's see if that works. Here we go, 100, 200. Now let's say that I wanted to add two vectors together. So maybe I have p1 and p2, and maybe this is like 1,000, and this is 300, right? So I could make another vector, which just goes vec2, p3, and then I could say p1.x plus p2.x, and then as the y component, it would be p1.y plus p2.y. And now if I print out p3, what do I get? Well, I should get 1100, 500, hopefully, and I did. However, you can see how this would become quite cumbersome, right? This would be annoying to do after a while. So up here, what we could have is we could have an add function, right? So I can say vec2 add, and then the add function is going to take in a const reference to another vec2, and that's going to be v. And then, so what this means is that this add function is going to take in a vector and then add it to this one and return a copy of that result, okay? However, let's do it more of the C++ way and actually use the plus operator. So instead of add, we can say operator plus. And what that will do is whenever we use two vectors, we can actually call the plus operator on them. So first, let me show you what happens when I try and add two vectors together. So vec p3 equals p1 plus p2. So if I do that, oh, we get an error already, but let me just compile and see what that error says. It says, sorry, I don't know how to make this font bigger right now, but I'll just read it out. It says error binary plus vec2 does not define this operator or a conversion to a type acceptable to the predefined operator. So it basically just said, hey, this class that you just made doesn't have a plus operator. So let's add a plus operator to this class. Okay, so the plus operator is going to return a new vec2, as you would expect. So this is vec2 operator plus, and it's going to take in a const vec2 reference. And what I like to do here is RHS as a variable name, because it shows you that the thing that's passed in is the thing that's on the right-hand side, RHS, of this addition. So this, we're going to return a vec2, which is x plus RHS.x, y plus RHS.y. So what this does is whenever we use plus on this as an with another right-hand side operator, then we're going to return this. Someone says, why use a const reference as opposed to just a vec2 reference in this case? So why we use const here is because we don't want this function to be able to modify RHS, because the logic of this function should never modify the right-hand side. Okay, so the reason we use const reference is so that if I try and say RHS.x equals 10, and then I compile, it will say x cannot be modified because it is being accessed through a const object. All right? However, why are we using a reference here? Now that's a good point, because you actually probably shouldn't use a reference here. And the reason you shouldn't is because floats are 4 bytes, and the rule basically is if your data structure is 8 bytes or less, just pass it by copy than rather by reference. Because here, if we have a reference, then we have to dereference it. So technically, I should be doing this. Okay, and actually, when you pass a copy of something, it doesn't matter if it's const. So for a data structure that is of size 8 or less, if we want to be as optimal as possible, we just pass in that data structure. However, if these are doubles, then we start getting into this gray area where, like if we had 3 doubles, like X, Y, and Z, then we may actually see speed ups by passing in by reference, okay? So I'm just going to leave it as a const reference for now, with that caveat that you may actually see speed ups if you don't use it, if you don't use a reference. All right. So what's going to happen here? Well, let's see what happens. Now, okay, my little IntelliSense thing has gone away. So let's compile and run now. So we do, and we get 1100, 500. So what we've done is we've told C++, here's what should happen when we use the plus operator on 2 vectors. So this already has saved us a tremendous amount of programming time, right? So that's just a really good thing. Now, let's say we want to tell if 2 vectors are equal, right? So what would 2 equal vectors look like? Well, in our case, we would want vectors to be equal if both of their components are equal. So we can have a thing that's going to say bool operator equals, right? And then const vec2 RHS. And here we're going to return true if x equals RHS.x and y is equal to RHS.y. And now some people may really want to be pedantic and put the brackets around these, and that's fine. There's nothing wrong with that. So now we can print out here, for example, if P1 equal to P2, now we can like standard cout vectors are equal. Otherwise, we can print out vectors are not equal. So let's run that. And the vectors are not equal, right? Because we didn't set them up to be equal. And just to be sure, let's change them so they are equal. And there we go. There's our unit test. Vectors are equal. Perfect. Okay, I'm going to change those values back. Now, let's do something a little bit different. Let's say that we want to scale a vector. What does scaling a vector mean? Well, let's say we have a vector and we want to make it twice as long in the x and y location, or in the x and y components. So what we see there is we're going to return a vec2, and this operator here is going to be multiply. And instead of, this isn't going to take in a vec2 here, this is going to be a float, and this is going to be a scale. So what we're going to do here is we're going to return vec2, and it's x times scale, y times scale. There we go. So we see here that our operators don't need to just work on other vectors. We can pass arbitrary things into the parameters for these operators. So now let's do the following. So I no longer need this. So P3 is going to be equal to P1 plus P2. And now I'm going to say P3 equals P3 times 10. And then print it out and see what happens. Cool. So it's 10 times as much as it used to be. However, let's see what happens if I say P3 equals 10 times P3. Uh-oh, now we don't know what to do. And the reason for that is that the integer type in C++ doesn't know what to do with a right-hand side operator of type vec2. Okay? So when you do things like this, up here, we could reverse P2 and P1. And the reason we could reverse P2 and P1 is because P2 knows what to do with a right-hand side operator of type vec2. But down here, we've got two different types, and integer doesn't know what to do, or float doesn't know what to do with a vector, but a vector does know what to do with a float. Okay. Now, just to save space, I'm going to move these all to their own line. And sometimes we actually want to do this for like niceness when we have a bunch of functionality like this. I actually like doing this in some of my programs. It is just a little easier and cleaner to like organize things like this so you can match up vertically all the logic and stuff, if they're all very simple like this. But let's say that we're doing a lot of scaling, and just look at this. P3 equals P3 times 10. This is a little suboptimal. Well, why is it suboptimal? Because all we wanted to do was multiply P3's values by 10. But what did we actually do? Well, if we look up at the multiply operator, what we did was we took its x and its y, multiplied it by scale, then created a new vector object, and then returned it, and then set the value of the old thing equal to the value of the new thing. And so what we want to do sometimes is we want to do things... and similarly... Oh, yeah. So let me just show you that. So if I wanted to set the value of P3 on its own, then what I could do is have a void function, okay? That void function, maybe I call it scale. And this is going to take in a float scale, right? And then what this function is going to do is we're just going to say x is scaled by scale, and y is scaled by scale. So just like we can say plus equals, we can also say times equals. So what will happen here is I can just say p3.scale 10. And now this is, it's more efficient because we're not creating that new vector, returning that new vector, and then setting the value. Okay, so this should just work. Perfect. So we get the same answer as before. But here's a little tip that I kind of like. And let me do this with add. So I'm going to make an add function. Okay, so add is going to take in a float value. And all this is going to do is x plus equals val and y plus equal val. Oh my God, my auto formatting is killing me here. All right, so P3, I can call P3.add 10, right? So what will happen here? Okay, so I've gotten my P3, I've added 10 to each of them, and then I've printed it out. And that is my desired behavior. However, what if I wanted to add 10 again? Well, I could say P3.add 10, and then they should end in 20s, right? And trust me, I'm going somewhere with this. What if I want to add 10 again? Okay, well, I've got a lot of like code here, adding these 10s, but watch this. I find this really cool. And I learned this a while back, but I like how this can sometimes be useful. what if instead of having a void function, we return a reference to a vec2, and I return this. So I'm going to dereference the this pointer, okay, and return that. So I'm going to return a reference to myself via add. So let me do this with scale as well, vec2 reference, and then scale at the very end is going to return this as well. Now you might say, why in the hell would I do that? Okay, someone in the chat just said chaining, and watch. So what is the value of this? What actually gets returned here? Well, this is actually a reference to P3. And as is this, I don't need to have those parentheses. So if this is a reference to P3, I can say this dot add 10, dot add 10. And look, it works. Because each time I call add, I'm returning a reference to the original thing. And so I can keep doing this. So I could say p3.scale2.add10. And that's like a really cool way and a really functional, short way of chaining together these operations that has very minimal overhead and allows you to like easily read this line of code, which you can see now, okay, he doubled it and added 10. And so that's just a really cool thing that you can do in C++ that you can't do in some other languages, okay? All right, what else might we want to do? Well, so far we've been returning vec2s, but what about something like a distance, okay? So let's say now we are going to have a float return, and we want to get the distance between this vector and another vector. So here we've got const vec2 right-hand side. And so this is going to involve some math. So we insert Pythagoras here. Right? Now, I'm not going to type it out here because part of assignment 2 is actually implementing this. So this, what we could do, and we will use this pretty often in our games, is something like p3.dist p2, right? And that will return a float which represents the distance in two-dimensional space between point 3 and point 2. Alrighty. What else? There was something else that I wanted to do here. I can't remember what it was. What other operators should I have out there? Anyone else have any suggestions of what I could add here? Oh, let me show you this. Okay. So I haven't tried this yet, so I'm not sure if this 100% works, but we'll figure out the syntax together as I do this. Let's say, you see down here where I have like, where I printed this out? What if I wanted to have standard cout P3? What if I wanted cout to know how to print a vec2? Okay, so I think, geez, how do I do that again? Is it the this operator? So void operator, and then I put in, geez, standard of stream LHS or something like that. Is this how I do this? And now return. So I will say LHS. No, that can't be it. I'm doing this wrong. Standard O stream. Oh, that's an output file stream. All right. Oh, wow. People out there doing it for me. Great. So let's copy and paste this in here. Why do I need friend here? Do I need friend here? These are public variables, so I think we're fine. This is vec2. What's wrong with this? Expected a oh, okay. Do I have O stream here? I do. This is a great way to end the vector. and the vector, and the class. Too many parameters for this function. No, I don't need this. Yeah. That would be if I declared it outside. You're right. So now LHS, I could say, do I pass it in here or do I return a string and do that? So stream X, Y, return stream. That should be fine, right? So now down here, can I do this? Standard cout. Why can't I do that? Nope. No operator found. Oh, do I have to do that inside the cout class? Oh yeah, because this should be based on, yeah, this should be inside that. Okay, I see what you're saying. Sorry about that. So I got to declare this outside the class. You know what? I shouldn't have showed something. I will try and have that for you up in the code section. So just realize that you can do that. Hang on. Let me just go find this online real quick. This is a terrible way to end the lecture. I apologize. I should be fired. Oh, don't say that. All right. Yeah, that should be right. So let's just put the friend back in. I don't need that. Standard F string operator. OS. All right, let's see if this works. Thank you for posting it. We're all trying it here. This is vec2. All right. Perfect. Thank you. And sorry I didn't know the syntax for that. There we go. Okay. So what we can do, if we want to be able to send an object straight to the stream, okay? So I don't think friend is necessary. Friend would be necessary if we have... Well, it is necessary? Wow, okay. It is necessary. Oh, geez. Oh, sorry. Okay. There. Posted it in, black screen. Apologies for that. I was still Googling. So here we go. Friend, OStream, operator, left. We pass in the stream and the vector, and it's a little bit confusing syntax, but we're returning the result of passing the vector X and Y into that stream, then returning the stream. Then down here, I can say standard cout P3. So that's how we define that. The syntax is a little bit confusing. Don't worry about that right now. The point is, I just wanted to show you that you can do that. Yeah, you can do that. The last thing I wanted to show is for construct, and this is just another C++ thing, which is how to construct complex strings that you're going to be adding a lot of stuff to. And for stuff like that, here's what I use, and I think it's one of the more, they're called string streams. They're one of the more efficient ways. So let's say I want to create a string, which is like some text, then some variables, then some text, then some whatever. So you can say standard string stream and give it any variable. I just say SS. And then you can say string stream, pipe in, let's have a string here, name equals Dave, and then int age equals 38, right? So SS, my name is name, and I am age years old. Okay? So a string stream is another type of stream that we are sending data to. And then if I want to print that out, if I want to print out the contents of the stream, I can say standard cout ss.string. So that will give me the string corresponding to what is in the string stream. There we go. So my name is Dave, I'm 38 years old. And at some point in this class, you're going to have strings that you want to draw to the screen, like points, colon, here's your points, or lives remaining, here's that. And so this is what I recommend for doing things like that is to use a string stream and then return the string from the string stream, because it's just an efficient way of doing that. Someone said, if we can do the left-left operator, does that mean we can also support float operations to be the first, as in 1.2 times vec2? The short answer is, I'm sure that that's possible somehow. The actual answer is, I don't know the syntax off the top of my head. So if you just Google something like that, I'm sure Stack Overflow would be happy to answer that question. It's just that I don't want to spend my time right now doing that on Stack Overflow. Okie doke. So that was the lecture for today. That was an introduction to ECS. It seems like forever ago we were talking about ECS, and then we talked about this vec2 class. And here was my Googling of the overloading of that operator. But if we go back to this, the next class is going to be really cool. I really love giving the next lecture because, believe it or not, up until even 4th year in our computer science program here at Memorial, we don't do a lot of software engineering or design patterns. And we're going to do this entity manager, which is a factory pattern, and it's a factory that manages all of our entities for us. And it's going to make our lives so much easier that I am sure for the rest of your lives, whenever you write games or you write any software where entities are constructed and released or things are often changed around, you are going to go to a factory pattern for constructing and releasing those things. Because it's just like one of these turning points in your programming career when you figure out what a factory is, why it's important, and how to implement one. And it's just so much easier after that. Okay, so that's it for today. Keep working on your assignments. Your assignments are due a week from you watching this lecture. Okie doke. That's it for me, and I will see you next week in the next lecture.